Now this oxygen is also a good leaving group. Why? Well, when this oxygen leaves, it's going to have a negative charge. Oxygens don't usually like having negative charges, but the negative charge on this oxygen will be stabilized by resonance, because there's a resonance form where the negative charge will be on this oxygen. But remember, this will also be part of the leaving group. So there's another resonance form where the negative charge is on this oxygen. So this is a relatively good leaving group because there's two resonance forms that can stabilize the negative charge. Now this leaving group is not going to have any resonance forms, so it's not going to be as good a leaving group. And this is the worst leaving group of all. Oxygen doesn't, who would rather have a negative charge? Well, oxygen would rather have a negative charge relative to nitrogen because oxygen is more electronegative. So because the nitrogen has no resonance and it's the least electronegative, it's the least happy to be a leaving group of all of these. What this means is it's easy to go down the chart, but hard or impossible to go up the chart. There's no direct way to go from here to here or here to here, but you can go from here to here or here to here. The second language book has a good metaphor. It calls these L groups the wildcards, because we can simply take one L group and replace it with a different L group. However, you can only do that if you're going down. For example, you can take an X and replace it with an OR, or you can take an OR and replace it with an NH2. But there's no direct, easy way to replace an NH2 with an X. We need a trick for that because it's hard to go up the table. Here's the basic mechanism for all these reactions. You can see the basic mechanism is attack the carbonyl, reform the carbonyl. All that's happening is we attack the carbonyl, and then when we reform the carbonyl, the leaving group leaves. That's the basic reaction. But the difficult thing is that just like with aldehydes and ketones, there's all these confusing protonations and deprotonations. I didn't show any protonations or deprotonations here, but most reactions have protonations and deprotonations that make things confusing. So we'll have to see some of those possibilities. Some of these reactions require catalysts to help them go along, and some of the reactions don't require catalysts. Well, would we expect this at the top to require a catalyst? Probably not, because this is the most reactive. So the reactions for these two generally do not require catalysts. These two generally do not require catalysts. Reactions for esters usually require catalysts, although I can think of one exception. But these reactions usually require catalysts. And this reaction, for the most part, doesn't happen, right? This is at the bottom, so there's not much we can do with this. It's not very reactive. But if we were going to do something with this, I suppose we probably would use a catalyst.